The 60-meter band in the United States just changed. It now consists of 4 individual channels, each 2.8 kilohertz wide, and one 15 kilohertz wide band. Each of these bits of the 60-meter band has an effective radiated power limit. That's 100 watts effective radiated power on the 4 channels, and 9.15 watts effective radiated power on the 15 kilohertz wide band. The 60-meter band looks so weird because we just made these changes, we being, I guess, the United States, I don't work for the FCC anything, to harmonize what's allowed in the United States with what's allowed in most of the rest of the world. And most of the rest of the world has this 15 kilohertz wide band at 9.15 watts effective radiated power. But in the United States, we also get these 4 channels because that's what the 60-meter band used to look like, and we get them at 100 watts, which is nice. So, how do we calculate effective radiated power? We've got some guidance here, and it is that for the purpose of computing effective radiated power, transmitter PEP, peak envelope power, will be multiplied by the antenna gain relative to a half-wave dipole antenna. A half-wave dipole antenna will be presumed to have a gain of 1, 0 decibels dipole. So this is kind of tough because usually antenna gain is given in not just unitless gain like this, and not in decibels dipole, but in dBi, decibels relative to an isotropic radiator. For instance, I modeled a quarter wave vertical antenna for the 60-meter band in software called EasyNEC, and it gave me the gain in dBi. That's 0.18 dBi, decibels relative to an isotropic radiator. So, to go from dBi to unitless antenna gain so that we can do the calculation as specified here, we do this. We plug antenna gain in dBi into this formula, run through it, and that gets us unitless gain. We then multiply the power setting on our transceiver by that, and we see whether or not we are successfully complying with the ERP power limits that we have of 9.15 watts for the band and 100 watts for the 4 channels. Here we're back to my little quarter wave vertical that I modeled in EasyNEC, and a quarter wave vertical is basically just a piece of wire a quarter wavelength long sticking out of the ground straight up like this. And according to EasyNEC, over the ground I chose, the type of ground matters, things like that, I have a gain of 0.18 decibels isotropic. So let's plug that into the gain formula here to get antenna gain relative to a half-wave dipole. So that would be (10 to the 0.18). We're filling that in from here. What the software calculated as the gain. Subtract 2.15, and what that does, that subtraction of 2.15, it converts this from decibels relative to an isotropic radiator to decibels relative to a dipole. And then the rest of this equation is converting decibels into just unitless gain. So going through this, that would be negative 1.97 for 10 to the 0.197. That is 0.64. We'll just round it off to the last 2 digits there. So now, going back to the guidance we have the gain of our antenna, and so we multiply that by transmitter PEP. So let's say I'm using my quarter wave vertical here, and I want to set my transmitter to, let's say, 20 watts. 20 watts. So we multiply 20 watts times 0.64 from here, the antenna's gain relative to a dipole, and that gives us, what is that? That's about 2/3. So that's going to be about 13 watts. And 13 watts, remember, is good for the 4 channels here, because 13 watts is less than 100 watts, but it's not good by the 15 kilohertz wide band here. So I can use these channels, and indeed I can use a lot more power on these channels if I want to, but I can't use this 15 kilohertz wide band at the 20 watt power setting on my transceiver. If instead I used 10 watts, 10 watts times 0.64 is just going to be 6.4 watts ERP. And 6.4 watts, of course, is less than 9.15 watts, so I can set my transceiver to 10 watts and use it on the 15 kilohertz wideband with my nice little quarter wave vertical antenna here. And so obviously, you can easily just divide 9.15 watts or 100 watts by your gain, and that will give you the maximum transmitter power you're allowed to use. So you don't have to do this calculation every single time. You can just figure out for a given antenna what the maximum power you can use and just stay underneath that. So let's try this for a different antenna. I have here an inverted-vee dipole antenna. If we were looking at it from the side, we have looks kind of like this, and it's up pretty high. The center is up 39 feet above the ground. So this is a pretty good antenna. You can see we get 5.28 decibels isotropic of gain, which is pretty nice. So let's run this calculation though for this inverted-vee dipole up 39 feet. So anyway, 10 to the 5.28 minus 2.15. So we're converting it from decibels isotropic to decibels dipole. Then the rest of the equation takes us from decibels to regular unitless gain. 10 to the 10. So our gain is pretty solid. Our gain is 2.06. And remember, we assume the gain of a half-wave dipole is only 1. So this inverted-vee dipole up 39 feet is more efficient, and not efficient necessarily, but more efficient or directional than a regular dipole antenna. And that's because it's over ground here, and that's having some impact on the radiation. Anyway, so let's say that we want to operate this on the 15 kilohertz wide band here, which has a maximum effective radiated power of 9.15 watts. So what we can do, let's figure out what the maximum power we can set our transceiver to is. So we take 9.15 watts, divide that by the gain of our antenna relative to a dipole, and that gets us, I'm just going to assume it's 2 for the purpose of ease and round down. That takes us down to about 4.5 watts. That's the maximum power we can set our transceiver to and use it on the 15 kilohertz wide band here. We of course can set it to higher power for one of the 2.8 kilohertz wide channels. Now I want to do the calculations for one final antenna. And this is an NVIS dipole. NVIS, NVIS, means Near Vertical Incidental Skywave. I modeled an NVIS antenna that's 4 feet off the ground, which is just a little more than a meter. And it has very low gain. The gain of this antenna is negative 3.94 decibels isotropic. And remember, we've got an antenna here that's very close to the ground. We're looking at this like a side view. So that's only 4 feet. And so the ground is having a big impact on this antenna, and it's really keeping the gain low. So, plugging this all in So the gain is only 0.25 relative to a half-wave dipole. So that's pretty low. So let's say that we're out there, we're doing NVIS with this low gain antenna. We're on maybe 5.45 megahertz, so that's one of the channels. And we're doing single sideband. We're going to do upper sideband because that's standard on 60 meters. Because this is 2.4 kilohertz wide, we're using a 2.8 kilohertz filter on the sideband. And we are going to tune it because it's upper sideband 1.5 kilohertz below the center of this band, which is at 5.405 megahertz. So we're going to be at 5.4035 megahertz upper sideband. We're going to be putting out 100 watts PEP from the transceiver. So the transceiver is set to 100 watts. Anyway, so 100 watts from the transceiver times 0.25 equals 25 watts effective radiated power. And that's less than the 100 watts we're allowed to. Indeed, it's a lot less. We could put 400 watts out of our transceiver if we wanted to, and we could still keep it legal. 400 watts out of the transceiver, with gain being 0.25, would be right at the 100 watt limit. So my thinking is that for people who are running NVIS antennas, trying to do near vertical incidental skywave, it's good for them to choose to be on one of the 2.8 kilohertz wide channels because you get that full 100 watt ERP limit, and you can really fine tune how much power you're putting out so that you have the minimum amount needed to make your connection. You might ask yourself, why do we care about these effective radiated power limits? Why does it matter if I'm putting out 100 watts of effective radiated power inside the 15 kilohertz band, something like that? So first and foremost, this is a small band. 15 kilohertz is super narrow, and the four 2.8 kilohertz wide channels don't add a whole lot to this. This is barely 25 kilohertz total of spectrum. That's not a lot. This is going to be a kind of crowded area, so we have to share it effectively with each other. Also, ham radio operators are not the primary users of this bit of the spectrum. We are secondary users. This can go away if people abuse it. It's also worth noting that in addition to the FCC being involved here, the National Telecommunications and Information Administration is involved in regulating a lot of this, because there are a ton of users inside the 60-meter band. For instance, I pulled some licenses online. Whatever this is, National Grid USA Service Company has a license to operate inside this band. The city of Lafayette, Louisiana has a license to operate inside this band. And this NVIS company has a license to operate inside this band. There are hundreds, if not thousands, of other users with licenses in here. So if we abuse it, and if people are acting foolish and blasting a lot of radiation they don't need to, interfering with primary users, then this can go away. So in closing, please be careful how you're operating. Do your ERP calculations so you're not blasting too much interference out there for anybody else, and have fun.